Good morning, Physics 20. I hope you guys are doing well today. We are going to begin the last lesson of the unit. And so, ladies and gentlemen, do you guys know what that means? Last mandatory lesson of the unit, of the course. That and the unit. So, ladies and gentlemen, all of the lesson videos after this one are going to be optional to you guys because we are now shut down for COVID. And because we're shut down for COVID, it means that we've had to cut down some objectives to the course. I'll continue making videos, and if you guys have any questions regarding what should be done, needs to be done, wants to be done, etc. from this point onward, let me know. All right. So, ladies and gentlemen, this is a very important topic. It also is going to come back a little bit next year. Not so much the actual gravity portion itself, but more the skills that you're going to be using here are going to come back in full force in our second unit in Physics 30. All right. So, ladies and gentlemen, enjoy your pun. You plan it for a party in space. Awesome. I love that. Little planets there are so cute. All right. So, ladies and gentlemen, I need to grab my pen. There we go. So, ladies and gentlemen, when something is going to be in orbit around another object, technically speaking, they're constantly falling. They're in like perpetual free fall. They're not falling towards the Earth or the Sun, but falling around it. Okay? So falling around it. So because objects are falling around it, they often appear to be weightless. Okay? Just continual free fall. It's pretty cool. So ladies and gentlemen, it is the gravitational force that is going to be our centripetal force, because remember, centripetal force is the force that pulls all objects towards the center of a circular motion, circular pattern, and it's going to be keeping the object moving in a circle. Okay? So, ladies and gentlemen, because of that, Sc is going to equal Fg. All right. So, ladies and gentlemen, this is going to be your strategy, okay, for all of the orbit questions that we are going to be looking at in this unit. All right. And I'm fairly certain there's at least 2 orbit questions on your assignment. Okay, so the second you see the word orbit is those questions, and they're the last set of questions on the assignment, you're going to bust out this strategy. Sounds good, guys? Alrighty-o. So we can expand our Fc equals Fg to do a whole variety of calculations depending on the scenario presented. Okay, so first of all, we're going to look at 3 of them. So Fc equals Fg. Well, we can look at Fc. Well, remember, Fc is the sum of all center-seeking forces. So it can be MAC. Fg is you're able to have, well, Mg. Now, ladies and gentlemen, I want you guys to be aware of this here. This is the mass of the object that is going to be accelerating. This is the mass of the object that, guess what, is inside that gravitational field. They're the same. So, ladies and gentlemen, these masses cancel. Okay? Remember, your AC can equal V squared over R. So one of the possibilities we could use is our V squared over R equals G. Now, ladies and gentlemen, this particular equation has a lot fewer uses than the other 2 we're going to look at. The reason why is because with this one, you would have to know the value of G. You would need to know the value of the gravitational field strength at that location. And the second you move anywhere away from the center of that object, G's going to change. Okay, G is only 9.81 when you're close to the center of the Earth. Okay, close to the center of the Earth, close to the surface of the Earth. That's what we're trying to say. So you have to know G at the location of the orbiting object. So because of that, ladies and gentlemen, we're not going to be using that one that much. We're going to be using the other two. I'm going to switch colors because I can, so it's a little bit easier for you guys to distinguish which one is here. The other option we can use is still going to be FC equals FG. But remember, ladies and gentlemen, we do have another equation for FG. So FC is still MAC. FG can be G M1 M2 over R squared. Okay, now that one is a lot more useful to us. Okay, the reason why is because, well, you don't need to know the gravitational field at any particular location. You need to know the masses and the radius, which can be determined. So this here, remember, is the mass of the object moving in a circle. This one here, ladies and gentlemen, is the mass of the object in the field. They're the same. They're on both sides of the equal sign. We can cancel them out here. So that would mean my AC is equal to G M2 over R squared. M2 is the mass of the object creating the field. AC can equal V squared over R. And then G M2 over R squared. So, ladies and gentlemen, we have another thing that we can cancel now. Look at this. We have an R squared on the bottom here and an R on the bottom here. That can cancel. So V squared is going to equal to G M2 over R. Okay, so you can use this equation so long as you have the mass of the object that is being orbited around, such as the Earth or the Sun or what have you, and the radius, so how far away or how far above the surface that object is orbiting. Okay, so this one is very useful. However, it'll help us calculate the speed of an object that is in orbit. That may not be the only thing you want to calculate. So I'm going to switch back to red. We can look at another way to approach this. So same idea that our FC equals FG for an object in orbit. FC is still MAC. And we're still going to be using this equation. So our, back here. There we go. G M1 M2 over R squared. So, however, remember, ladies and gentlemen, there's another equation for AC. First, I am going to cancel just as I did before. I'm going to cancel out those M's. Okay, same idea. These masses are the same. This is the mass of the object that is accelerating. This is the mass of the object in that field. They're the same. We can cancel them. Now, AC, remember, ladies and gentlemen, our other equation can be 4 pi squared R divided by the period squared. Well, will then equal GM2 over R squared. Okay, so ladies and gentlemen, well, I cannot cancel my radii here. Okay, I can't cancel my radii. Why? One's on the top and the R squared is on the bottom. They don't cancel across like this, but I can rearrange this. I'm going to multiply both sides by R squared. Okay, so if I multiply both sides by R squared, I have 4 pi squared R cubed over T squared is going to equal GM2. Look at this, ladies and gentlemen. Remember the previous video that we looked at? Look at this. R cubed over T squared. What do you see there? What does that look familiar to? Newton's laws based off of Kepler. Isn't that awesome? I love it. Love it. Okay. So, ladies and gentlemen, what we've got is Kepler. Okay. He's showing up in Newton's laws. Okay, they're linked. So, ladies and gentlemen, evidence that even scientists don't go at it alone. Okay? So, as Sir Isaac Newton said, if I have seen but a little further, it is by standing on the shoulders of giants. So, what he meant by that is if he was able to create these laws and come up with these ideas, it wasn't him alone, right? He had, oh, hi Freya, he had the help and support of other brilliant people around him that he was able to draw off of their ideas. Okay? All right. So, there's your inspirational speech for the day. Hi, Freya. She's showing me her treat ball. Yes, this was supposed to keep her busy while I'm filming videos so she wouldn't be bugging me. You go get it. You go play with your treat ball. So much for that, eh? Now I dropped my stylus. There it is. Okay. Ladies and gentlemen, back to physics. All right. So, ladies and gentlemen, these are the letters for your equations. And M1, the mass of the object in orbit. M2, the object being orbited, units are kilograms. R is the radius from the center of each object. Okay, so if we have, there's the, Earth, there's the moon. This is not to scale. If you're going to be determining, using the Earth and the moon as an example for a calculation, you need to know the radius of both the Earth and the moon. Okay, the moon or radius of the moon will be given to you. Okay, so ladies and gentlemen, on the orbital radius of Earth, data sheet. G, back of your data sheet, nothing's changed. Little g, gravitational field strength, newtons per kilogram, or meters per second squared. Okay, so ladies and gentlemen, this is really important here. As we showed above, you do not need the mass of the orbiting object to find its speed or its radius. Okay, so you don't need the mass of the orbiting object to find the period either. So ladies and gentlemen, that is why I've been hounding on cases where you are going to have to be equating stuff, because in this case, and on your assignment, I definitely give you at least one of these. I do not give you the mass of the orbiting object, so you have to substitute. You can't find FC and then go and equate it to FG, because you won't be able to, because there is no mass. Okay, so no mass of the object doing the orbiting. So the strategy I showed above may be where you have to start and you have to equate it. Okay? All right. So, ladies and gentlemen, let us begin doing some calculations. So calculate the speed of an artificial satellite in orbit. The second you see that word orbit is the second you are going to start out with FC equals FG. Right away. No question. That's where you start. So calculate the speed. We can now calculate the speed. That is this high above the surface of the Earth. Okay. So I'm going to need to calculate my radius here. Okay. So my radius, ladies and gentlemen, before I start, okay, I got to convert that into meters before I do anything. Okay, so my 1.6 times 10 to the power of 3 kilometers, I'm going to multiply that by 10 to the power of 3 meters over 1 kilometer. And I'm going to get 1.6 times 10 to the power of 6 meters. Now, this isn't my actual total radius. This is the radius of how far we are above the Earth. So we can call that radius of the satellite, I guess. Well, our radius total is going to be the sum of the radius of Earth plus the sum of how high above the Earth the satellite is. It's the R total that we need to use. This is one of the most common mistakes I see with this calculation, is just grabbing this number and using it right out of the gate. Please don't do that. You'll make me cry inside. Okay, so I am going to add my radius of Earth from the back of my data sheet, all right, to my value up here. So the radius of Earth, 6.37 times 10 to the power of 6 meters, plus 1.6 times 10 to the power of 6 meters. And I am going to get a total radius of 7.97 times 10 to the power of 6 meters. That is the value that you're going to use in your calculations. Okay, so you've been asked to calculate the speed. Well, remember that FC is equal to MAC, FG, GM1, M2 over R squared. Now I have to use this one, ladies and gentlemen, because I have not been given G that high above the surface of the Earth. Okay, 9.81 can only be used when you're close to the surface of the Earth. Okay, when we're in orbit, 9.81 just doesn't apply anymore, guys. All right. Well, I've been asked to calculate speed. Masses cancel. So the value for the AC, the equation is going to be this one. Okay. Because the other equation doesn't have speed in it. So GM2 over R squared. All right. Well, the radii are on the bottom. This radius cancels. V squared is equal to GM2 over R. I've been asked to calculate speed, square root both sides. Okay, so that's the equation I'm left with. Now I'm going to put my numbers in. And now M2 is the mass of Earth. Where do you get the mass of Earth? Data sheet. All right, so V are 6.67 times 10 to the power of negative 11 multiplied by the mass of Earth, which is 5.97 times 10 to the power of 24. I'm going to divide this by the radius, 7.97 times 10 to the power of 6. Don't square it now because you've already canceled it. I accidentally wrote the squared there. Let's get rid of that. There we go. So you've already dealt with the squared by it being canceled out, so you don't have to square it this time. And then you're going to square root the equation, and you are going to get 7068.39 ... meters per second. Now, sig digs, units, all that good stuff. I want 3 sig digs, so you're going to need to put this in scientific notation. 7.07 times 10 to the 3 meters per second. Okie dokie. Not too shabby. So I know these questions are a little bit tricky. There's kind of a lot to them. So sign up on Google Meet if you guys have any questions. All right. Calculate the time in hours it takes the satellite to orbit Earth. All right, so now this is another tricky question here because I have asked for time it takes for the satellite to circle Earth. So I can't, if you use V equals D over T, I'm going to sob. Okay, true sob. Don't use V equals D over T. Now we need to think though, because we are here doing circular motion. Remember that the time it takes, for that object to go once around its cycle is called the period. Okay, how long it takes a satellite to circle the Earth. How long does it take the satellite to go once around the Earth? So that means we've been asked to calculate the period, ladies and gentlemen. Well, we have already calculated VC from our previous question. All digits and counted in your calculator, so 7068.39 ... meters per second. Guess what you have? On your data sheet, you have VC is equal to 2 pi r over the period. We have VC. We have this. Swap them. Okay. You know what's funny? technically speaking, this equation is a variant of v equals d over t. So how I said don't use v equals d over t, well, the 2 pi r, guess what, ladies and gentlemen? That's the circumference equation. Okay, that's the equation for circumference. Remember, circumference is the definition of circumference is the perimeter of a circle, which means it's the distance that's traveled if an object is going to be going around there. So that technically is equal to v equals d over t. But at the same time, not really, because we don't have the distance that's traveled. Isn't that cool? Isn't physics grand? Okay, so ladies and gentlemen, 2 pi r, you have 2, we have pi, and once again, do not use 3.14, use that button in your calculator. If you put in 3.14, I'm going to be sad, okay? And then the radius, once again, which we calculated up here, okay, is our 7.97 times 10 to the power of 6 meters. And we're going to divide that by our period. I forgot to rearrange this, so we'll rearrange it now. So t is equal to 2 pi times 7.97 times 10 to the power of 6 meters. And we're going to divide that by VC, which we have. Okay, so which is this value here. So 7068.39 ... all your numbers in your calculator, please and thank you. And once you put this into your calculator correctly, please, we are going to wind up with a 1. Whoopsie. Okay. We wind up with 7084.63 ... seconds. Ladies and gentlemen, the speed is meters per second. Our units up here are meters. The units are meters per second. Our time is going to be in seconds. Now, this is an awkward thing to use with, and the question said in hours. So this is not useful to us until we convert it. So, ladies and gentlemen, we're going to convert this. In 1 hour, there are 3,600 seconds. Those cancel. And then we are going to be left with 1.9679 hours. I'm going to write over here, for sake of space, sig digs, units. We're going to wind up with 1.97 hours. Sounds good? Okay. All right, ladies and gentlemen, next question. Whoopsie. Come on, question, get back here. There it is. Alrighty-o, ladies and gentlemen. We've got a new scenario. A planet is orbiting a star with an orbital radius of that many meters. It takes the planet 7.6 days to make a complete orbit around the star. What is the mass of the star? Okay. Note my wording here in the question, orbital radius. In this case, ladies and gentlemen, I've just given you R straight up. Okay. There is nothing fancy here with the R. 9.72 times 10 to the power of 9 meters. So if you see the word orbital radius, that is R. If I say above the surface of Earth, you need to add the value I give you to the radius of Earth. For question 2, I've neither given you the name of the planet nor the name of the star. You don't have enough info to do any of the other bits. So therefore, I've given you the orbital radius. Okay? So that's R. If the planet takes 7.6 days to make a complete orbit around the star, what is the mass of the star? This is actually how we can estimate the mass of our sun. Isn't that cool? So you can't just like saunter over there and plonk it on a scale. Okay? It doesn't work like that. Okay? So ladies and gentlemen, we have a period of 7.6 days. Okay, now this isn't helpful. Our radius is in meters. Our standard units are meters per second. We got to convert this into seconds. Well, ladies and gentlemen, how many hours are in a day? There are 24 hours in one day. How many seconds are in an hour? Now look, days cancel. We are then left with our units of hours. And now we need to look at getting this into seconds. There are 3,600 seconds in 1 hour. Units cancel. We're left with seconds. Success. And we're going to get us our period, which is 6.5. I dropped a 5. 6.5664 times 10 to the 5 seconds. Keep all digits in your calculator. We're going to need them. Okay. We've been asked to calculate the mass of the star. Well, we've said the word orbit. Okay. That means your strategy, FC equals FG. Okay. FC is equal to MAC. FG, GM1, M2 over R squared. This is the mass of the planet orbiting the sun. This is the mass of the planet. They cancel. Now, I've got the period here and I don't have speed, ladies and gentlemen. What do I need to do? I have to use my other equation. I have to use 4 pi squared r over period squared is equal to gm2 over r squared. You've been asked to find the mass of the star, so that's m2. You're going to multiply this side by r squared and divide by g. Okay, so those cancel, and we are going to be left with 4 pi squared. Squared plus another value is going to give you cubed, so by 4 r cubed, and then g times t squared is going to equal m2. Okay, so ladies and gentlemen, what we're going to do is plonk our numbers in and solve, and once again, be careful of putting these guys in your calculator. Lots of squaring and cubing going on here, so take your time, no panicking. So 4 pi squared, okay, we're going to leave that. Our radius, okay, that I have given to you. It's cubed. Cube it. Divide by 6.67 times 10 to the power of negative 11 for big G, multiplied by the period squared. We calculated the period here. Okay. Carefully putting this in your calculator. 4 pi squared, bracket, this number, bracket, cubed, enter. Bracket, this number times this number squared, enter. Okay? Well, close your bracket at the end. Be cautious with your calculations here in the calculator. All right, M2. Once you get this in your calculator correctly, 1.2606 times 10 to the 30 kilogram. Power of 30. It's a huge number. So ladies and gentlemen, let's think for a moment before we put this into sig digs and units. The thing with physics is our numbers need to make sense at all times. Why does this number make sense for this scenario? Good, because it's a star. Stars are ridiculously huge. They are massive, massive, massive items. And it's just mind-boggling how big these objects really, really, truly are. So, ladies and gentlemen, it is okay to have a large number for this. You want to have a large number for this. If we got 15 kilograms, we'd have a problem. Okay? All right, so let's get this number into sig digs. So on the question, I have given you 3 sig digs, so I want 3 sig digs. 1.26 times 10 to the power of 30 kilograms. All right, sounds good, ladies and gentlemen? All righty-o. All right, I'm just going to pause for a sec. I'll be right back. All right, I'm back. Sorry, guys. I was trying to find my scale model marbles of Earth, the Earth, Moon, and Mars, so I could kind of give you an idea of actually truly how massive the planets are in the solar system. Sadly, I can't find them when I need them. They always turn up when I'm not looking for them. So anyway, once I find them, I'll pull them out and make a separate video on them. But I'll give you guys an analogy just to show you how big our sun is and why a number like this makes sense. Like, it's so hard to imagine how big the sun is. And our sun is really not that impressive of a sun or a star, really. It's kind of average size, maybe. So, okay, we're back. More technical glitches. We're good. So fortunately, we were done our calculations. So ladies and gentlemen, what I was attempting to explain here was why that really, really large number makes sense and how big our sun actually is. So we had calculated the mass of this random star to be 1.26 times 10 to the power of 30 kilograms. Now, that's a ridiculously huge number. So let's think about an analogy to represent how big our sun is, how much mass it has in comparison to the mass of the entire solar system. So our sun contains 99.8% of the mass of the whole solar system. Let's put this into apples. Imagine a basket of 100 apples. These 100 apples represents the percentage of the mass of the solar system. Of this big basket of 100 apples, take out one, cut out 1/8 of one apple, and put that remaining 7/8 back. Okay? About 1/8. So, ladies and gentlemen, we have approximately 1/8 of an apple. Now, Jupiter and Saturn alone, they represent like 90% of the mass of the planets in the solar system. So if you take that remaining bit and you cut that little tiny wedge in half, each of them would be about maybe approximately the mass of Jupiter and Saturn each. Put those aside. Where is everything else in the solar system? The mass of Mercury, Venus, Earth, Mars, the asteroid belt, and Uranus, and Neptune, and Pluto. The mass of all of those in this analogy is accounted for as the juice of the apple that sticks to the knife that you have cut the apple with. Isn't that insanity? So the mass of Earth in comparison to the mass of our sun is irrelevant, is completely insignificant. Let's see, an analogy that I can come up with that would also make sense. I've got some D&D dice on my desk here. So let's say this green D20 here, so this 20-sided dice, is the mass of the Earth, or the size of the Earth, excuse me. Well, the size of the sun would be bigger than my office. Way bigger than my office, probably bigger than our classroom. So we just look around the room that I'm in as far as you can see in the camera, and there's the Earth. And the size of the sun is bigger than my office if this is the Earth. So it's mind-blowing to think of how big the sun is and how tiny the Earth is. So it's just bizarre. And we're not even a major planet in our solar system mass-wise and size-wise. And our sun isn't really that exciting of a sun. It's pretty minor. And the size of our sun is tiny compared to other ones like Betelgeuse, and that's not even the biggest one. So it's mind-boggling. I'll put a video in Google Classroom to kind of give you a visual of how small our sun really is in the universe. Like it's mind-blowing. All right, so ladies and gentlemen, enough with me giving you guys existential crises on how tiny the Earth is. So there are some practice problems for you guys. Give some of those a shot. And ladies and gentlemen, this is the last mandatory video of Physics 20 for you guys. I know it's gone by so fast. I mean, what day is it today? Today is, for me, it's May 26th. So whenever you guys are watching this, it's going to be a different day. But we've got like less than a month of school left, and until the due date is left. Due date is done, and you guys know grad is next week on Friday. So crazy. It's just gone by fast in spite of the shutdown. All right, guys, I hope you all have a good day. No fires, injuries, or explosions. And even if you're not going to do that last assignment, I hope you guys still watch the videos just for fun, for your physics edification. Have a good day, guys. Bye. Now I can't find the stop button. All right, see you later.